Next week, we'll hear from Jason Schenkel, who will tell us about the history of computer games. Today I have the pleasure of introducing you to Mehrdad Aliasgari from our sister branch in Long Beach, one of the largest CSUs. And he's going to introduce us to the computation, secure computation. So let's welcome our speaker.
Thank you, Dr. Ledin. Thank you so much for coming. I want to talk about secure computation and its applications in today's world and the challenges that come with secure computation, right? But let me begin by asking a question. What is the first thing that comes to your mind when you hear security? Just first thing pops up. Don't think too much. Encryption. What else? Failure. Right, that's a good one. What else we have? Okay. Well, encryption is a very good one. Failure, of course, we have to admit to that one, right? And accept that that's a good one too. Usually people think of malware. Dr. Ledin is an expert in malware, viruses, ransomware. Big word today. Everyone talks about it. Identity theft, I put it there because of Equifax, right? We all heard about it. Social Security is gone. Some other people might think about network security. We hear every now and then about distributed of denial of service attacks and other attacks related to the way that the internet functions. But to me, this is security, right? Because I just flew. I had to go through TSA, right? And you know what they tell you, right? You know, take everything off, right? Put it on the belt, right? And when you think about it, these guys are doing as much security as we cybersecurity experts do, right? What they're doing essentially, they're providing protection for valuable assets, right? Now their assets in this case are airplanes, right? Planes and people on it, and probably the baggage, right? For us, our assets are different forms. We can think of data as being one of our assets, right? So when you think about identity theft and Equifax, the asset was the sensitive information that they were storing on their databases related to your credit score, your social security and whatnot, right? That's an asset. We need to protect it, right? When you think about software is an asset, right? Well, it's a piece of work that you have done, you program it, right? And you need to protect it, right? So no one can steal it, no one can use it in a way that you don't plan for it, right? Hardware is an asset, right? You want to make sure that your routers are working, all of your hardware is functioning the way that you want it, right? And no one attacks it. Communication links is another asset, right? Like, you want to make sure the adversary doesn't come and floods or jams your channel, right? Or in a sense, denial of service attack is an attack that your channel is gone, is lost, bombarded, and your servers are shut down, right? And you can't provide the services, and so you're being targeted. So security is like, well, we have the assets, and let's go and actually protect these assets, right? That they're really valuable to us, right? And for these guys, the assets are the planes, right? And so, to me, my focus is I choose information or data to be my assets, right? And so the talk is focused on that type of asset and trying to see what we can do in that regard, right? And so when you think about information, you have to think about what are the stages or states that information can be, right? Information is either a transit. I'm sending a message to you. You know, I say, hey guys, let's meet in this room and have a chat. And so I want to protect that information, right? And so securing the information and transition is a challenge and something that we have been working. So the gentleman who said encryption, that's perfect. You just came up with an answer or a solution to protect information at transit, right? And so when you see that padlock when you go on your website, when you go to gmail.com, that green padlock sometimes, which we call it transport layer security, right, or TLS or SSL. What we are doing, we are actually protecting information at that level, and we come up with solutions. Encryption is one solution. We use encryption to protect the asset there. And information could be also at the storage, right? So that social security numbers at Equifax, they were stored in a database, right, or somewhere. And we need to think about how we are going to protect them while the data is at rest, right? And one of the solutions we have is also encryption. Encryption does help a lot, but we could do more than that, right? But my talk is about the last one. When the information is at the computation stage, when you're actually performing computation on the data, right? And the goal here is that we want to protect the information while there's a computation happening on it, right? And so what is secure computation? If you think about it, it's about data, protecting data while it's being computed. So it means that I have some valuable asset to me, which is a sensitive private information, and I want to make sure that when someone runs a computation on it, right, they're not going to learn more than what they're supposed to learn about the nature of the data and the content of the data, right? So I'm already talking about having more people involved. I have data, someone else does something on it, right? And I want to make sure that guy doesn't find out what I have, right? It looks like as if this is a type of work, a field that you're dealing with multiple entries. And so if I was going to define it's like when two or more parties, they have their own data. They want to come together and perform a computation jointly, right? And learn the outcome of the computation, find out the result of that computation without revealing anything about their input, right? So you want to run your credit card query, credit score query. Your input is your social security number. You want someone to run a credit card on you, but you don't want them to find out what is your social security number, right? That's like an example of secure computation. And I already actually said two or more. And the reason we say two or more, because we found out later on when we started looking at this area, we found out that we have to separate or divide this area into two categories when there are only two parties involved, like you and me, right? Or when there are more than two parties involved. The reason behind it is like the solutions that we come up with these and two scenarios are drastically different. So we separate them and put them into two categories. In the two-category computation, you have Alice and Bob. Alice has her input X, Bob has his input Y. They want to run a joint computation. This blue box is a computation. They want to run this joint computation together and find out outcomes, A and B. They could be either the same or could be different. But the idea is that Bob shouldn't figure out anything about X. All Bob is going to find out is his B, and vice versa. Ali shouldn't figure out anything about Y. All she knows at the end of that whole task is like the result that was assigned to her, right, the A. When you have multiple party, you have more people. They all bring inputs, right? They don't have to provide, but they could provide inputs, and it could be like an array of data. And now they start talking to each other, and there's like a lot of conversation going on here. They talk to each other, send data back and forth, and at the end they learn something about a function of their data and other people's data, right? And that's all they have to learn. We have to guarantee that there's nothing else, right? So if this is an adversary here, right, or this guy's an adversary, right, they both look bad to me. If this guy's an adversary, all she's going to find out is the result of that computation, nothing else about any other input, right? And so what we have to do, we're actually solving a puzzle now, right? So we have to come up with a protocol, with an algorithm that involves people talking or interacting, right? The concept of interaction. They send each other. They say, okay, this is for you. Now go and do something to it and come back to me. And then I do something to what you sent me and send it back to you. That level of interaction. We do that. At the end, we want to learn something but you're not going to learn more than what you are supposed to learn. You know what is interesting is that once you actually think about secure computation, you can think about it, you know what, we could actually extend the definition of secure computation to include secure outsourcing. And so the idea here is you have a client or a combination of clients, and for whatever reason, they have a task that they don't want to run themselves. They have a data, they have a function for that data, but they're computationally too weak, or they don't have the resources to run it, so they want to outsource that task to someone else, right? They want to hire Amazon Web Services and say, hey guys, you go and run that computation because you're so powerful, I pay you, right? I pay you in CPU hours or something, I pay you, but you run this computation for me. But it turns out that data I have is very private. It's patient records. I'm a hospital, don't have the power to do things by myself, or I don't have the knowledge to do it, but I own the data. The data turned out to be very sensitive. I'm going to hire Amazon, but federal law requires me to protect the privacy of my patients, so I have to, when I want to outsource it, I have to make sure that it's done securely, right? So I send the task to a bunch of servers. It could be a bunch of them, or it could be just one server. You could just have one Amazon node or multiple Amazon nodes. And you run them, and they run your task, they do things, they come back with the result of the task, right? And they learn nothing, right? And you just pay them. Bless you. I sometimes say, when I was learning this, when I was a student, I was learning about this, I thought of this as blind cooking, right? I don't know about you guys, but let's say, and this actually is the case in my family. Let's say you have a valuable secret recipe that you inherited from your great-great-grandmother, right? Let's say that happens to be the case in some family. So you have this recipe, you want to keep it secret, but you're going to throw a party of 100 people, right? It's a big wedding, right? And you want to hire a cook, right, to do this, but you don't want the cook to see what you're doing, right? Because you inherited this recipe that was supposed to stay in the family, right? So the cook, in this case, the cook is actually doing blind cooking, right? So it's closing their eyes. They don't know what they're doing, right? They say, okay, the protocol says grab this, put it here, turn the heat on, right? Wait 10 minutes, then pour it into this, right? They don't know. They touch things, they play around with things. They don't know what they're doing at the end is that dish, right? You get the dish and you give it to your friends and they're all happy, and you keep your recipe secret, or the ingredients to that recipe you can think of as data, that to be protected. It is really challenging, right? It's kind of a weird thing to think about. It's like, well, in this example you can see there's a messy kitchen right there, because cooking blindly doesn't work for humans, but performing computation blindly turns out actually could work for us, right? So where things began, I want to give you a little bit of a history, right? And maybe we can think about this for a little bit. Where things began. Secure computation actually turns out to be something that is not new at all. In fact, a gentleman from Stanford, Andrew Yao, they praise him to be the founding father of secure computation, because he was the first guy to come up with the solution. And what he was trying to solve is that millionaires problem. That happened in 1982, before you and me were born, right? So in 1982, he said, this millionaires problem is bothering me. So the idea of this problem is that there's Alice and Bob, they're very rich, they belong to the upper class, right? And you know what rich people do? They're jealous. They want to know who is richer, who has more money, right? So Alice says, I am richer. Bob says, no, ain't that way. I own more. And they want to figure out who owns more in their bank account, right? But you know what rich people, you know how they are? They don't want to reveal their data, right? How much money they have in their bank account. That account balance is the private data, right? Computation, this. Right? You have seen that comparison? As the simplest computation, right? I want to know if A is bigger than B. If A is bigger, Alice is richer. Output Alice. As a result, I was output Bob, right? Or maybe in the case of tie, flip a coin or do something, right? And so that's called the meaningless problem. Yao actually came up with the solution in 1982, and that's why he's contributed to be the founding father. But the problem was that the solution that he came up with was too costly. In a more detailed way, the solution that he had was exponentially, it had the exponential complexity with respect to the size of those two variables, right? And from your algorithm courses, if you ever take, you find out that we don't like those algorithms that have exponential complexity because they ran forever, right? And it takes too long. But this is a challenge, right? This is a puzzle. Like if I was going to ask you guys, like, okay, go and come up with an answer to this puzzle. It is a puzzle, right? If I was going to ask you go and come up with an answer to this puzzle, you will notice immediately it is no easy task to deal with, right? It's a very complicated puzzle, right? It looks very simple. Who is richer, Alice or Bob? But it's very complicated. Because you have to make sure that the adversary, let's say if Bob is the adversary, he's not going to find out anything about A, but he's going to find out in this. And then how do you know that's the case? You actually have to mathematically prove that Bob is not going to find out anything about Alice. There's no information leakage. That there's nothing about, he's not learning anything other than what he's supposed to be learning, right? You have to mathematically show that, and that's the challenge. In cryptography, we say you have to do three things. You have to define your problem. You define the context of what you're doing. You have to define your assumptions, and then you have to actually provide a mathematical proof. Usually it's contradiction. Provide a mathematical proof that your solution is actually achieving the goals that you have, right? And so when you try to do that, you see it's very difficult. In 1982, I think the best solution that I know, 2011, was published, right? 29 years, let's say 30 years, round it up. 30 years on, we're still working on this problem, right? And we have some solutions, we're trying to make it more and more practical to have lower complexity and be useful. So, okay, the problem, let's say, is defined. So we know roughly what secure computation means. So what are the adversaries that I need to protect? Remember, in TSA, our adversaries are quite unknown, known, right? So those bad people who are trying to smuggle something into the plane and do things, right? Here I have to actually very well define who are my enemies, so then I can go after them, right? In secure computation, we divide our enemies into two categories: passive adversary and active adversary. Passive adversary is an adversary that she's curious. She actually listens to the protocol. So when you define the protocol, it says these are the steps that you have to do for that blind cooking. The adversary actually follows the protocol, but she wants to learn about the ingredients, right? Out of the curiosity, wants to learn about the data, but is honest in the sense that it actually follows the instructions. That goes against active adversary, an adversary that doesn't have to follow the protocol the way she was told to. Maybe you say, grab this ingredient and put it into the pot. Well, they won't do that. They put something else into the pot, right? And now, and they do it intentionally to figure out what was the thing that you asked them to put into the pot to cook, right? And that's the active adversary. It's a much more challenging adversary. We call them sometimes malicious adversary, because maliciously they're trying to screw things up and make the system fail. Right? These are more powerful adversaries because they could cause more damage. These are more limited adversaries, right? And it's actually a lot easier to go after this adversary and then this adversary. So it's a lot harder to protect against a malicious adversary. All right, we have adversaries. Let's talk about the tools. You know, just like secure transmission that or secure storage that we talk about, it's like, all right, we know what we want to do. Let's build a tool that provides a solution for us. And someone said, let's use encryption, which is perfect, right? We also need to have tools, but in this case, we actually need to come up with new tools, the tools that you have never seen before, right? And so I'm going to put here 4 tools here that are very widely used in this area. One of them is called homomorphic encryption. And that's actually a relatively new tool. It is a type of an encryption. And, but it has a property. It does what encryption does, which turns things into gibberish, in a meaningless thing, so no one can actually understand what they mean unless you have the key to decrypt, right? Homomorphic encryption, they do that, and on top of that, they say, hey, I have another property. You know what? If you take an encryption of one message and you take an encryption of another message, and you do an operation, let's say you multiply them in the ciphertext domain, what you get at the end is the encryption of the 2 plaintexts summed together, right? That is actually secure computation, right? I have 2 things, I don't know what they are, put them together, what I get is something else that is actually sum of the 2 things that I didn't know, right? And I still don't know what that thing is, because it's still encrypted, right? So it's still in encrypted format. So mathematicians came up with encryptions that provide us that characteristic, and it's a lot of math, not for today, right? Another tool that we have, which is quite powerful. This tool, we usually use it for 2-party setting. Right? Another tool that we have, which is quite powerful, is called secret sharing. That's the case when you have more than 2 parties. Right? So it's like, let's say the whole class, we want to come together, we want to figure out who has the highest GPA. Right? You have your GPAs, you don't want to reveal, I don't know why, right? But you don't want to shout it out, right? But we want to like basically run a maximum algorithm on this array of GPAs, right? Each of us has an array. What we could do, we could actually get our input and break it into pieces and then distribute it to everyone. Now each piece looks like random noise or randomness. So if you have just one piece, you can't make sense of it. It looks to you gibberish, right? But if I scatter my GPA across, like, I don't know, let's say there are 50 people here, or 30, I scatter through 30 pieces, each one of you guys get a piece of it, and you can't make sense of it. But once all of you come together, you can actually reconstruct the actual data. Then you will find out what my GPA is. So long as not all of you are against me, I don't know, I hope that's not the case, but let's say not all of you are against me, then you're not going to find out what is my GPA, right? Because you're missing one piece, right? At least one piece or more, right? And so secret sharing is a very good tool, because if you have a multi-party scenario, each entry can actually distribute the data that way, and then they can actually run computation on the shares, and then at the end merge them together and reconstruct the result, right? And that will be usually our protocol. Right. There's another tool that is quite popular, and it's actually one of the first tools that we came up with. It's called oblivious transfer. And that works for 2-party. The idea behind it is that, let's say you own a data, right? Let's say you own a pair of data, like S0 and S1, right? And I want to find only one of them, right? I want to select only one of these 2 pieces of data that you own. Of course, I can come to you and say, give me S0, right? And you can give it to me. But what will happen after that is that then you find out which one I selected, right? What if my input was valuable? That index, either 0 or 1, was a valuable thing to me, and I didn't want you to find out what that index is. I want to actually select only one of these 2, but you shouldn't see which one, right? And oblivious transfer is actually a very complicated protocol. It does make use of the homomorphic encryption and actually will achieve that, exactly that. I will select exactly one, not more. I don't select two, exactly one of your two data that you have, and you don't know which one I selected. And it will help us a lot. The last tool, which is probably very complicated, it is actually one of the most used tools. That's the one that solves the millionaire's problem. It's called garbled circuit, right? All of our best solutions for that one single computation of comparison, right, where the A is smaller than B, usually is implemented this way. And so garbled circuit says, you know what, any computation is a Boolean circuit. At the end of the day, it's just a bunch of AND, OR, XOR, you know, all these things. And you get a bunch of inputs, you run it through the circuit, and at the end you get a bunch of other Boolean values, and that will be your result, right? And so what if I actually create my Boolean circuit, right? I have input wires for each gate. Let's say here's an AND gate. And then I have an output wire for each gate. And what I do, instead of like having a truth table for that gate, if 0, 0 comes, it's 0. If 0, 1 comes, it's 0, and so forth. Instead of giving you a truth table, I give you a masked in a sense of encryption, encrypted truth table, right? And what I do, I replace zeros and ones with random strings, and your truth table is actually an encryption of labels. We call these labels, right? And so when you try to evaluate, so someone will generate this circuit and gives it to another party to evaluate the circuit, and the other party will say, okay, I have this label, I don't know what that means, and I have another label for this wire, and I have this label for the other wire. I know what that means, but these two form a key to decrypt exactly one of these rows of my truth table, my new truth table. And then I decrypt that, and the result is the label of the output wire. And now I move on to the next gate. And I do that for every gate, right? Now you don't know what you're doing. You're cooking blindly, right? The labels have no meaning, randomness. But someone actually knows what that randomness means. Someone generated that randomness, that random looking protocol. And at the end, actually, you get to calculate you get to execute your circuit, your Boolean circuit. And that's exactly how we solve the millionaire's problem. Or so far, that's exactly what we have done, right? So that's secure computation. Now I want to talk quickly about the application of it. To me, the application for secure computation has been about mainly focused on biometrics, right? What are biometrics? You have seen them. You probably use them if you have iPhone or Samsung phones, the fingerprint, Apple Face ID that is new, whatnot. These are all dealing with biometrics, right? And so what happens in biometric is that you have a biometric which is a characteristic just unique to you. You're the only one who has that fingerprint, right? And so you enroll one time, you grab your phone, you do it like 10 times, whatever Apple says, and data is extracted, it's stored on your phone. Next time you want to go and log in, you do the same thing. A template or a set of features are extracted from your biometric, and we run a computation. That's where I come in. We run a matching computation, right, between the template you gave and the template that's already there, right? And if it's a match, we say, okay, you're authenticated. If it's not matched, we say, please leave. Right? You don't belong here. Right? Let me pass that. But before I talk about, don't do that for two-factor authentication, right? That's not what it means, the social security and credit card. But let's talk about authentication and how we actually authenticate, right? So there are usually 3 ways of authentication. There is either passwords, right? Pins, things that you can memorize, right? You can remember them, so hopefully. But the challenge with them is that we notice that humans have a problem with choosing good passwords, right? If you look up the top passwords, number one is actually password, right? And then it's 1, 2, 3, 4, and it's like football, you know, and so forth, right? And so then we say, I'll make it hard to guess. So I'll put that as special character, lowercase, uppercase, number here, 16 characters. We put so many restrictions on it that no one can remember it, right? When it becomes hard to guess, it becomes hard to remember. And then let's admit who is here who says that they haven't recycled the password, meaning that they haven't used the same password for 2 services, right? Who is here to have the same password for their Gmail and Facebook, right? Don't raise your hand, right? But let's say that that's a challenge, because once one of them is compromised somewhere, the adversary knows that you're recycling it, right? You're reusing it, right? So they go after all of your services. Then the other method that we have is hardware-based solutions, like the tokens, the smart cards, and whatnot. So you go and actually present a hardware solution. It could be a Bluetooth-enabled necklace or something. But and they usually work. They're better than passwords. Problem is that you have to actually have that thing with you all the time. Don't leave it at home. And if you leave it in your car and your car gets broken and stolen, well, go and change it, right? And so that's a challenge that, you know, they could be stolen or left. So we moved immediately without thinking too much. We, as the industry, we moved to biometrics. We said biometrics are cool. Biometrics are easy because it's something with you. You always have it with you. It's not like you're going to leave your face at home, right? Well, most likely you carry it with you around, right? And you don't need to remember how you look like, right? You don't have to even think about how you look like. It doesn't have to be hard to guess. It doesn't have to be hard to remember, right? And so biometrics became super, super popular. Now the challenge with biometrics, and I have it right there. What is the biggest problem with biometrics? What does it mean that they are irrevocable?
Change your face.
Exactly. You can change that. My password is compromised, I go and reset it. My card is stolen, I go and reset it. My fingerprint is compromised, I go and reset it. No, I can't do that, right? I can't, well, unless you do plastic surgery, but it's very difficult to change this, or your iris, or your voice, once it's out there, it's out there, right? So if an adversary sees or gets a hand on your biometric, you're in trouble, right? Forever, right? And that's why they are extremely valuable. They're arguably more valuable than the other two, right? The other two, we get rid of them if they're compromised. Maybe we don't pay that much attention. But this guy is valuable, and it runs a lot of computation. So actually it runs some secure computation on it. The other thing about biometrics is that biometrics reveal some data about you. You know, if you use DNA as your biometric, well, you are your DNA, right? There's everything about your family, everything is in your DNA, right? If you use your face, there's so much I can learn about you. I can run the data mining and figure out your ethnicity, your gender, your age, roughly. You know, I can learn so much about that. Maybe you don't want people to find those things out either, right? Maybe you want to protect that type of information. So goal is to protect biometrics while they are being computed to run biometric match algorithms. Immediately we hit a challenge, too complicated. There are too many different biometric types, too many different algorithms, too many different computation on it, and so it's not that easy. So what I did with my colleagues, we started breaking these things down. We started solving them one at a time. And we started like a long time ago to focus on iris matching, long before Samsung introduced that iris thing. And we said that let's actually try to come up with a solution that you can compare your iris to another iris in a secure way. You keep it to yourself, and the other iris stays the same to themselves, and you just learn the result of match or not, right? And we also look at iris outsourcing and how we actually outsource computation on iris matching when you have one server on Amazon or you have multiple servers on Amazon. And we published the results there. We found out that one server is practically takes too long, right? And so it's almost impractical to run it. When you actually hire multiple servers that they don't all collude, they don't all come together, it becomes a little bit more practical. Right? Then we went after DNA. Around the same time, we look at the particular computation of DNA outsourcing, and then after that, we moved on to voice. That's work that we have been doing about your voice and another computation. Turns out that it actually uses a completely different thing than everything else. It's actually represented using floating point numbers. So the representation is floating point. The other ones usually were integers. We had to rebuild whole solutions on it and come up with a very, very different different solutions for particular machine learning algorithms like hidden Markov models that I don't want to get into them. But the solutions that we have come up with, they mainly work for speaker recognition. When you're trying to figure out who this person is as opposed to what they said, right? Speech recognition is what they said, right? And so we published that. Recently, we have been working on Fingerprint, right? And Fingerprint is an interesting and very challenging thing, is because you have these minutiae, all these tiny things, these nodes that represent the curvature and the angle of your pattern, your fingerprint pattern. And what it is, when you try to compare two fingerprints, you actually have to first align them, because you could put your fingerprint in different angles. You could put it like that, or you could put it flat, right? And so you have to try to align the fingerprints and then do a match. And it turns out to be a super complicated task to run this fingerprint secure fingerprint matching, alignment and matching. And so I skip it, but we found out to do is that we decided to use fixed point representation to do this as opposed to floating point representation. Okay? And we got some result that was recently submitted. But let's talk about performance, and that's the actual challenge about it. And I want to put here some charts. These solutions that I've been talking about, they are really costly. So I put some few here. This is one example of secure division, like two floating point numbers divided together and you get another floating point. This is an operation that you don't think about it because it's so simple to you, right? It takes milliseconds to finish when you actually see the raw data. But when you don't see the raw data, right, when you're doing it in a secure way, when you have a passive adversary using secret sharing, the complexity actually goes high. If you're running only one division, right, or a few divisions, in a fixed point, in a floating point, it could take, I don't have it here, it could take like 80 milliseconds, which is a lot higher than normal without any security. And we did like complex operations, logarithm exponentiation, and on this axis I have to say when you do a bunch of them together, when you batch, instead of doing one calculator computation, you do like thousands of exponentiations. You try to batch them all together. You actually get a better performance. But it runs 160 milliseconds to just do one exponentiation, right? And let me go quickly through these things. That less than, that comparison, billionaire's problem, and this is another really depressing charge actually, because when you look at when we implemented our solutions, when you have the active adversary, right, in a two-party case, active adversary, our comparison, when we run one comparison, it takes about 1.4 to 1.4 seconds, okay, to just run one comparison. And again, when you run it on your own phone, it is a millisecond. Here it is 1,000 times worse, and that's the challenge, right? The solutions work, but they are quite challenging. This is another thing, execution of fingerprint matching. This is also a little bit depressing, I guess, right? When you look at fingerprint matching and alignment, the one that I talk about, in a two-party scenario, when your adversary is passive, right? These are the sizes of the fingerprints, right? But it could take up to 84 or 83 seconds to just do a comparison. Now, if I was going to tell a teenager that in order for you to unlock your phone, you have to wait 84 seconds on your iPhone, I don't think that teenager will appreciate what we are doing. We'll throw that away. It's like, give me that. I want to reveal my fingerprint. I don't care, right? And so, because right now on your iPhone, it takes a matter of milliseconds up to like, I don't know, maybe 100 milliseconds to just unlock your phone. For us, we're saying that, hey, if you want to put protection on it, that's the price, right? And the challenge, and this is a work that we're going to publish with, hopefully very soon. And these are another ones, another examples. But the challenge here is the feasibility and practicality of it, right? And that's what we are trying to do. We are trying to make our solutions every time better, perform better, and be faster than before. But what are the other applications of secure computation? So far, we have talked about just biometrics. However, you could do it for everything else. First example comes to my mind, I think, is the financial sector, right? A lot of these companies, banks, if they actually were implementing our solutions, they wouldn't need to have access to your raw data. Then you wouldn't need to trust them. And hopefully the Equifax wouldn't have happened, right? So they could just run a query on your credit card or credit score without actually figuring out what your social security number is, right? So these are some credit card fraud detection is another one. That a lot of these banks, if they can come together, they can actually detect the fraud before anything happens. But unfortunately, banks do not like each other, right? I don't know why, but it looks like there is something between them. Distributed of denied service attack, I mentioned earlier on. If the internet service providers actually could perform a secure computation, they could detect that early on and shut it down. But you know what they don't do? Because they don't want to share their private user data with each other. Verizon and AT&T have no good relationship, right? And so they don't want to share with each other. So they say, well, we can't run the computation. But if that tool that we actually used for speaker recognition, we found out that they can take our solution and modify it and optimize it a little bit to detect denial of service attack. So far, they haven't taken it, but hopefully that's the direction to go. Personally, I'm also interested in these other topics to go for. Speech recognition, neural networks. Within the speaker, we want to focus on speech recognition, so you don't have to trust Siri anymore. You can say what you want to Alexa or Siri and have no worries. You can use Google Translate without Google knowing what you're doing, so they can't use that later on in court against you. Also, the other thing is that how we can actually verify that the original input is actually trusted. Like the original fingerprint is truly a fingerprint that belongs to a human being, right? And that actually is a whole different challenge on a whole different level. And another thing that we have had a good level of success is trying to automate these protocols, right? So you programmer come to me and say, this is my program without any security, go and make it blind. That blind cookie, make it to run in a secure fashion. So these are other protocols I'm looking for. And if you have any question, I'm available to talk. And also there's my homepage to go and check it out.
One or two questions.
was sort of a urban legend going around in previous years about people being able to pull fingerprints off of photos of hands.
Yeah.
Was that the sort of inspiration for people trying to verify that fingerprints were coming from people, or?
Oh, if unfortunately, if people, and I think there was an example of the Minister of the Defense Ministry of Germany.
Yeah.
Is that an example?
Yeah.
That she had her hands like that, and they took a picture of a high resolution and stole. Yeah, if that happens, there's not much that you can do unless put gloves on, right? What we are trying to do is basically when you enroll for a service and you're protecting your fingerprint or your face or your DNA or voice, and you want to authenticate yourself to someone else. That's where the inspiration comes. Right now, for all of these services, you actually have to, the way every of these companies are doing these things, from Samsung up to Apple, everyone else, they actually run raw data. They run the computation on raw data. They require you to give a raw data. That's why when you enroll, there's a lot of those terms of services that no one reads, and you just click agree, agree. But what that means at the end of the day is that they gain ownership of your actual raw data, right? And this happens with Siri, with Alexa, with everything else. So our inspiration is that I want you to talk to Alexa, and Alexa goes to Amazon services and comes back with the song that you asked to play, but I don't want Alexa to know what you said or also find out who you are, right? And don't run any of these privacy violations that they run data mining to figure out, to violate your privacy and track you and do all sorts of things. That is one of the main inspirations behind it. Yes?
So you mentioned the Alice versus Paul problem initially took exponential complexity.
Yeah.
What was the complexity of the garbled circuit?
The garbled circuit, I can't remember right now. And also those solutions that we implemented, I forgot to mention that we implemented them on a normal desktop, right? So like a normal Intel 5 CPU, like an average Mac, right? Not anything like super fancy or anything. Of course, if you have a higher, better resources, those numbers will go down. I can't remember the exact all complexity of that one, but I think it runs on for in just below a second, a millisecond, for a normal the normal desktop.
Okay, well, thank you very much.